It's my pleasure this evening to introduce 4 people, and the way we're organizing it is I will introduce everyone right now at the beginning, and then they will go in order of my introduction, and then when we finish the talks, we will actually, all 4 speakers will join me on the stage for a question and answer session, and then, as I mentioned, we'll all go upstairs for a glass of wine. So, Nancy Pick, our first speaker, who is in fact the author of The Rarest of the Rare. She is a former staff writer for the Harvard Museum of Natural History, an author, editor, and translator. Her book, Curious Footprints, tells the story of how Amherst College professor Edward Hitchcock amassed the world's largest collection of dinosaur tracks, even though he did not actually believe the footprints were dinosaurs, but he collected them anyway. Nancy's next book, Stig and Etta, will be published in 2017 in Sweden, and in it 2 women cross paths. One follows the trail of her famous father, a Swedish writer lost to suicide. The other traces her anarchist cousin who barely survived the Holocaust. And together the 2 women discover a shocking play that pits one against the other. So if you see her later on, you can ask her more about that. Currently, she is also writing an illustrated history of Amherst College, and Nancy is also a fellow of the Linnean Society of London. Our second speaker, Raquel Alonso Perez, is the curator of the Mineralogical and Geological Museum here at Harvard. She is responsible for access to, teaching, research, public education, and continued development of the world-class earth science collections we have here. She received her BS in geology from the University of Granada in Spain, her PhD in earth sciences from the Swiss Federal Institute of Technology in Zurich, Switzerland, and her teaching strengths are optical mineralogy and gemology. Her main research interests are mineralogy and petrology, with a special focus on the geochemistry of ore and gem deposits, and we're going to be hearing about some gems this evening, in more ways than one, actually. So Don Pfister, our third speaker, has been at Harvard for over 40 years. He teaches about fungi and plants, and his curatorial duties center on the Farlow Library and Herbarium, Harvard's collections of algae, mosses, liverworts, lichens, fungi, and several other groups that all used to be called cryptogams, not cryptograms. I made that mistake once, Don. That's why he's put it in parentheses for me. His research is on a group of Ascomycetes fungi that are often referred to as the Discomycetes, or cup fungi. He is interested in understanding relations within the group and their biology. He has also written on topics dealing with documentation of collections and history, most recently Charles Darwin's involvement in a potato breeding programs following the potato famine. During his time at Harvard, he has served as director of the Harvard University Herbaria on several occasions, and in fact this evening is standing in as Chuck Davis, the current director of the Herbaria, is on sabbatical. And he would say that his long service at Harvard has only led to more service at Harvard. And he has been, among many things, Dean of the Summer School, Master of Kirkland House, and Interim Dean of Harvard College, and too many committees to name, which I can attest to. Our final speaker, James Hanken, is Alexander Agassiz Professor of Zoology and Director of the Harvard Museum of Comparative Zoology. He received A.B. and PhD degrees in zoology from the University of California at Berkeley, and then worked at Dalhousie University in Nova Scotia and was a faculty member at the University of Colorado in Boulder. He moved to Harvard in 1999. His research focuses on the evolutionary morphology, development, and systematics of vertebrates, especially amphibians. His lab has maintained active field programs in Africa, Asia, and Central and South America. He has authored more than 125 scientific publications and edited 4 books. He is an accomplished nature and scientific photographer, and his photographs have appeared in several books, field guides, and magazines, and hear this, including Natural History, Geo, Audubon, National Geographic World, and finally, Playboy. And I'm not going to ask what that was about. So anyhow, without further ado, I introduce the first of our 4 speakers, Nancy Pick. Thank you.
Once, when I was giving a tour of the Natural History Museum here, a woman came up and handed me a set of postcards. She was an art teacher, and she liked bringing students to the museum to sketch. She was so pleased with one student's drawings that she made them into postcards, including this one, which happens to depict a specimen featured in the Rarest of the Rare. Terrible thing in a jar. The back of the postcard identifies the young artist as Emily and the terrible thing as Bathynomus giganteus. It seems, however, that Emily was better at art than at biology, because Bathynomus giganteus is a big deep-sea isopod, a foot-long crustacean that looks something like a giant pillbug. And in fact, there are currently some on display in the arthropod exhibition next door. But the terrible thing in a jar must be something else entirely, for it appears to have neither an exoskeleton nor any legs at all. Terrible thing in a jar. I saved Emily's postcard all these years because I thought her drawing was delightful, and I loved that phrase. But what is the animal in the jar, really? And why do I consider it one of the most fascinating among Harvard's 21 million natural history specimens? I will return to that in a moment. The Rarest of the Rare was first published in 2004. The team working on the book had decided that it should showcase 60 specimens of animals, plants, and minerals from Harvard's vast collections. Some specimens had historic significance, some had scientific importance, and some simply had a good story to tell. Choosing the specimens for the book was a long process, a kind of treasure hunt, one that had already begun before I came on board as writer. There were a few surprises along the way. I think back to the day I went to talk to a curator in invertebrate paleontology, and he said, "You know, we have a fossil sand dollar you might be interested in. I'm pretty sure it was collected by Darwin." Of course, since that time, and in the decades since the book came out, there have been many changes at the Harvard Museum of Natural History. The smell, for one. One of the pleasures of writing this book was finding all the poems inspired by Harvard's natural history collections. My favorite I chose for the book's epigraph. Struck dumb by love among the walruses and whales, the off-white polar bear with stuffing missing, the mastodons like muddy buses. I sniff the moth-proof air and lack for nothing. The thing is, that's still the way I feel when I walk into the museum. And I know I'm not the only one. The poet simply fell in love with the place, and so did I. And that feeling is what I sought to capture in The Rarest of the Rare. That feeling remains the same. But yes, there have been changes. In 2009, in honor of the museum's 150th anniversary, the Mammal Hall was renovated. The hall used to reek of mothballs, the poem's moth-proof air. I'd like to think there's still a slight perfume of paradichlorobenzene remaining, just a hint, but the odor is definitely much reduced. After I had a good draft of the book written, I sent the manuscript around to many scientists here, and there was only one entry that raised eyebrows. Some scientists said that it did not deserve a place in the book because the science it described was too speculative. This was the piece on the thylacine, popularly known as the Tasmanian tiger. Scientists in Australia, where there was much guilt about the Tasmanian tiger's extinction, were extracting DNA from museum specimens in hopes of reconstructing the animal's genome and ultimately bringing it back from extinction. In the end, none other than Edward O. Wilson said we should keep the essay in the book, because even if the science wasn't there yet, it might move in that direction. It seems that, as he often is, Ed Wilson was right. In 2012, there was even a new word coined that has gained some traction, de-extinction. In perhaps the most dramatic development, as you may have heard, Harvard Medical School professor George Church has gotten very serious about his project to bring back a version of the woolly mammoth. Earlier this year, Church's woolly mammoth revival team successfully took genes from a long-frozen mammoth specimen, specifically genes for hemoglobin, fat, and hair, and inserted them into the DNA of Asian elephant skin cells. They used a genome editing tool called CRISPR, developed in large part at Harvard, and the subject of an article in the New York Times Magazine just last weekend. Church's vision calls for creating a hybrid animal, I call it a mammothant, that would graze what is now tundra, supposedly helping to insulate the melting permafrost and counteract climate change. Wow. That makes the Tasmanian tiger project look pretty tame. Interestingly, scientists are making efforts to revive several extinct species featured in the Rarest of the Rare, including, and these are Mark Sloan's beautiful photographs from the book, the Carolina Parakeet, the only parrot native to eastern North America, the Xerxes blue butterfly, and I can tell you that seeing and photographing these lost butterfly specimens was truly heartbreaking. And the gastric brooding frog, whose life cycle was nothing short of amazing. A female would swallow up to 25 fertilized eggs, which would develop in her stomach. Her entire digestive system would shut down, and after 6 or 7 weeks, the froglets would emerge from her mouth and hop away. These de-extinction efforts remain controversial at a time when some argue money might be better spent researching and protecting the many endangered species that are struggling to stay alive. Still, the quest is tantalizing in a Jurassic Park kind of way. Extinction is very much on the minds of scientists these days, and in the public eye as well. As you perhaps know, a terrific book by New Yorker writer Elizabeth Kolbert titled The Sixth Extinction, try and say that 3 times fast, won the Pulitzer Prize this year, about how we are on the brink of a mass extinction caused by none other than us, Homo sapiens. Returning to the topic of terrible thing in a jar, here's another possibility. Nabokov's genitalia cabinet. Vladimir Nabokov, the Russian-born novelist most famous for Lolita, worked in the entomology department at Harvard from 1942 to 1948. He spent many, many hours dissecting the male genitalia of the butterflies known as blues in order to distinguish species that looked virtually identical to the naked eye. And when he was done dissecting, he put each organ, technically known as an oediogus, into a little glass jar and stored them in this cabinet. Clearly, he was passionate about his work in butterfly systematics, and he was a good scientist, although ultimately, literature won out. In a letter to his sister during his time at Harvard, he wrote, "To know that no one before you has seen an organ you are examining, to trace relationships that have occurred to no one before, to immerse yourself in the wondrous crystalline world of the microscope, where silence reigns, circumscribed by its own horizon, a blindingly white arena. All this is so enticing, I cannot describe it." Although, of course, he just did. This is Nabokov's drawing of male butterfly genitalia, in case you were curious. Uncensored, Jim. Here at Harvard, biologist Naomi Pierce has carried on Nabokov's tradition of studying blue butterflies. She has assessed his scientific work in a book due out next spring from Yale called Fine Lines, Vladimir Nabokov's Scientific Art. In her essay, she mentions that his most remarkable contribution to science was his reorganization of a group of neotropical blues, splitting them into 9 genera, 7 of them entirely new. Nabokov hoped, before he wrote Lolita, that his scientific work would preserve his name for posterity. He was quite excited about discovering a new butterfly species in France in 1938, which he called Lysandra cormian. He then wrote a poem about it a few years later that was published in The New Yorker. Note that a type specimen here is the official representative of a species. On discovering a butterfly, I found it and I named it, being versed in taxonomic Latin, thus became godfather to an insect and its first describer, and I want no other fame. Wide open on its pin, though fast asleep, and safe from creeping relatives and rust, in the secluded stronghold where we keep type specimens, it will transcend its dust. Unfortunately for Nabokov, in 1989, this butterfly was discovered to be a hybrid of 2 other species. And so it will likely not endure as a distinct species itself. So much for posterity. Still, I'm happy to report that the entry on Nabokov's genitalia cabinet in Rarest of the Rare has spawned a number of other publications and has, in this sense, endured. Nabokov's cabinet is featured in the book Secret Museum, Some Treasures Are Too Precious to Display. It also appears in Atlas Obscura, an online magazine that calls itself the definitive guide to the world's wondrous and curious places. And his cabinet is even mentioned in Nabokov's Wikipedia entry. In terms of Rarest's afterlife, even beyond Nabokov, last spring I attended a conference at Radcliffe called The University as Collector. And when I went up to Harvard history professor Laurel Thatcher Ulrich afterwards to thank her for her wonderful keynote address, she told me she had used the rarest of the rare in one of her courses. I nearly fell over. Her course, which aimed to get students doing research into Harvard's collections, was called Tangible Things, Discovering History Through Artworks, Artifacts, Scientific Specimens, and the Stuff Around You. I can only say that it's very gratifying to discover that your book has been useful, even several years after being published. And now I'm absolutely thrilled that Rarest has been given a new lease on life as a beautifully produced paperback. And I want to thank Jim Hanken, Director of the Museum of Comparative Zoology, and especially Jane Pickering, Executive Director of the Harvard Museums of Science and Culture, for their tireless efforts to get the books reissued. My sons would say that the terrible thing in a jar is my homemade cranberry sauce at Thanksgiving. I blame the rarest of the rare, and this specimen of the small cranberry collected by Henry David Thoreau. Thoreau describes in October of 1859 going a cranberrying in a Concord peat bog, aiming to have a dish of this sauce on the table at Thanksgiving of my own gathering. As he well knew, everything tastes better when you hunt for it yourself rather than buying it at Stop and Shop. He wrote, and as I quoted in Rarest, "Let your life be wholly without an object, though it be only to ascertain the flavor of a cranberry." This is quite a charge to action. Unfortunately, where I live in a suburb of Amherst, there are no cranberry bogs that I know of. But I do gather hickory nuts in the woods for my Thanksgiving stuffing, and just as Thoreau promised, the taste of them does indeed capture the flavor of life in New England. In terms of posterity, Thoreau's collection of pressed and dried plants, containing some 900 specimens he collected beginning in 1850, is now being scanned so that it will be available online through the Harvard Herbaria. The digitization of Harvard's natural history collections is perhaps the biggest change since Rarest first came out a decade ago, a major advance and a huge ongoing project, making Harvard's collections that much more accessible to the world. Okay, not to leave you hanging, this is the actual terrible thing in a jar, as photographed for Rarest of the Rare. It's a giant tube worm, Riftia pachyptilla, and the story of scientific discovery linked to it is one of my favorites in the book. As a first-year graduate student at Harvard, Colleen Cavanaugh had a eureka moment. In 1977, the deep-sea submersible Alvin had discovered giant tube worms living near a hydrothermal vent, where hot water shoots out of cracks in the ocean floor fed by undersea volcanoes. The tube worm presented a strange puzzle. It had no mouth. It had no anus. How did it survive? Cavanaugh solved the puzzle. In the middle of class, she jumped up and announced that there had to be symbiotic bacteria living inside the tube worms, producing their food for them. And she was exactly right. Just as plants derive energy from the sun through photosynthesis, the bacteria derive energy from chemosynthesis using sulfide. Thanks to these bacteria, the giant tube worms can survive deep in the sea without any light at all. Admittedly, the terrible thing looks terrible in its jar. Pale and unappealing, in alcohol, the specimen loses its color. But in the wild, giant tube worms are very beautiful. Some 6 feet tall with bright red tips, colored by hemoglobin, just like human blood. Scientists keep finding more hydrothermal vents and more surprises. Since that first view from Alvin, some 300 new species of animals have been discovered living in these communities. This is a new species of Yeti crab called Kiwa tyleri, discovered in the waters off Antarctica and officially described by science just this year. Its bristles act as a breeding ground for the bacteria they feed on, so the crabs grow their own garden. But I also want to step back and look at the big picture, which is perhaps even more exciting. Some scientists believe that life on Earth originated in deep-sea hydrothermal vents, where the chemicals and energy just might have provided exactly the right soup. So what's in my jar? not Louie Agassiz's turtle embryo pictured in this slide. Agassiz, as many of you know, founded the Museum of Comparative Zoology here in 1859. This is another of my favorite photographs from the book, and one of my favorite stories as well. But my time here is limited, so if you're curious, I'm afraid you'll just have to read the book. As Willy Wonka once said, so much time and so little to do. Wait a minute, strike that, reverse it. Anyway, I thought a long time about what to put in my jar. I thought perhaps nothing but alcohol. That way, the terrible thing would be imaginary, containing whichever specimen each of you finds most fascinating from this incredible museum here, and the stories that you associate with this place yourself. Also, I was thinking back to a specimen that we considered for Rarest, but in the end did not include in the book. In the Marine Invertebrates collection, there are jars containing jellyfish collected by Louie Agassiz in the mid-1800s, carefully labeled. But when you look through the glass, you see nothing at all. Zilch, nada. The jellyfish have dissolved over time. I often wondered whether they were really jars of nothing, saved only because their collector was famous. So a few weeks ago, I wrote to Adam Baldinger, who is collections manager of marine invertebrates, and I asked him about these jars. He thoughtfully replied, yes, over the years, the body of jellyfish can break apart. While the body form no longer exists, the tissues do remain. However, the quality of the tissues, cells, DNA, etc., depends upon the type of preservation used. And as jellies are generally fixed and preserved in formalin, the DNA has likely fragmented quite a bit. But researchers continue to develop useful tools that allow them to study DNA that is fragmented. So our specimens are, in most cases, not only of historic value, but have much scientific value as well. It struck me that Agassiz's specimens were collected before the discovery of DNA, and yet the museum preserved his jars nonetheless. And while these jars of jellyfish might have appeared worthless a century ago, with the passage of time, they have regained importance. I like that idea. And speaking of jellyfish, the new Marine Life exhibition that opens here next weekend will feature models of glowing jellies and interactive jelly displays. Nice. And I know that Jim Hanken happens to agree with me that the glass invertebrates made by the Blashkas are even more beautiful than the glass flowers. And there are currently many exquisite jellies on display next door made of glass. I've come to realize things in jars have a measure of immortality. I was just back in my Chicago hometown for my dad's 85th birthday. He's fading now, his memory failing, but he still loves plants. So I gave him a beautiful coffee table book called The Oldest Living Things in the World, which features a bristlecone pine in the California desert that has been dated by its rings to 5,063 years old. I was thinking a specimen from one of these would have been a good addition to Rarest of the Rare. Longevity was not a category we thought about years ago, 10 years ago, when we were younger. There is sadness in the natural world as we stand on the brink of so much loss, but there is also comfort in it. You feel that, and I feel that, every time I step through the door of the Harvard Museum of Natural History. Again, I think of Louie Agassiz. For all his flaws, he was an anti-evolutionist, for heaven's sakes, he must have been a wonderfully inspirational man. On the occasion of his 50th birthday, none other than Longfellow wrote a poem for him. Its refrain imagines nature as Agassiz's childhood nurse, singing to him the rhymes of the universe and keeping him young in spirit throughout his entire life. For whenever the way seemed long or his heart began to fail, she would sing a more wonderful song or tell a more marvelous tale. Longfellow captures the way that a natural history collection can take you everywhere in the world and even beyond it, a universe of possibilities, whether you are at the beginning of your lifespan or nearly at the end. Okay, here's my jar. Wait, no, I'm not done yet, though. Don't clap yet. Yes, I don't know if people can see. It's a real Harvard jar, but it's pretty small. It's Saturn. The Cassini space probe has been orbiting Saturn since 2004. Along the way, it has photographed Enceladus, one of Saturn's 62 moons, and sampled the jets that spew like geysers from its southern pole. Not only is Enceladus a bright object in the sky, because it's entirely covered in ice, making it white and reflective, but it's also very tantalizing. because scientists now believe that beneath its frozen surface, this moon may have a warm ocean, similar to a hydrothermal vent on Earth. And in that warm ocean, it's possible that there exists a chemical soup like those found on Earth near volcanoes in the deep sea, perhaps similar to where the terrible thing in the jar lives, the giant tube worm that survives without the need for light, and where, maybe, just maybe, life began. Harvard's Mineralogical collection already contains a piece of Mars in the form of a slice of meteorite. If it turns out that there is life on Enceladus, I fully expect that, well, as long as this life form isn't deadly to us Earthlings, Harvard will obtain a specimen of it. And that will be a very nice entry for Rarest of the Rare, Volume 2. An outtake. This is an alternative cover for Rarest of the Rare, one that was never used. It's a little irreverent. It shows an Epeornis egg from the elephant bird of Madagascar, which became extinct roughly 500 years ago, likely due to hunting. There are probably fewer than 24 intact elephant bird eggs left in the world, each holding the equivalent by volume of 180 chicken eggs. We had to be very, very careful photographing it for the book, for it is truly among the rarest of the rare. Thank you very much.
Good evening, everyone. It's a pleasure for me to speak tonight to you. And when I was asked to talk about a couple of specimens, treasure from the Mineralogical and Geological Museum, two items immediately stood out from me and from the more than 400,000 objects that we have in collections. And I'm glad to know that also those specimens were chosen 10 years ago and represented on Nancy's book, not just because of the rarity and the cultural impact, but also from the science behind them. So the first specimen I'm going to talk about belongs to the Hamling Collection. Hamling was a very knowledgeable and prominent man from Maine, to the point that his uncle was vice president to Abraham Lincoln. His connection to Harvard dates back to 1855 when he earned his degree at the medical school. And that was actually his main profession. He served as a surgeon during many different battles during the Civil War. Overseeing his father's mining operations, developed his creative artistic side, which produced drawings such as the catalog of gems and jewels. We have this manuscript in collections. But he not only designed those beautiful drawings, he also created outstanding jewelry pieces. This is the well-known Hamling Necklace. As you can see, the Hamling Necklace consists of a very single gold chain where there is 18 removable pendants of gem tourmalines of various colors. This necklace, all the tourmalines from the necklace were found in Mount Mica in Maine, which is considered the first deposit of pegmatite discovered in North America in 1820. This necklace is also considered the best North American jewelry piece of the 19th century. Hamling didn't really leave a concrete evidence of the initial drawings of the necklace, so we don't know how it was originally designed. However, the first picture that we have dates back to 1959 by Ursula Marvin. Ursula was not only the first research woman in geology at Harvard University, but was also the first woman that probably took the necklace out of collections, which is nowadays, I think. So really proud for her, she made it. This tourmaline necklace, along with a set of gem tourmalines, are not only important because of his beauty and his rarity, but also allow us to do research based on collections outside, so we support external research, but we also do it in-house. And I was able to study the causes of colors in tourmalines and also develop a dual technique based on Raman spectroscopy and laser ICP-MS data in order to refine the crystal structure of tourmaline. As you can see, described by the great Ruskin in 19th century, he described the chemistry of it is more like a medieval doctor's prescription than the making of a respectable minerals. And I'm not going to go into detail on the chemical structure because that could take probably the whole day. But we were able to define different positions within the chemistry, and also this dual technique has great potential for the gem industry, identifying gemstone treatment, and also natural versus artificial gemstones. My second specimens, which is probably the best, I would say the first, belongs to the Barrage Collection. In this picture, Barrage is the man sitting on your left, is sitting on his mineral room at his house in the Commonwealth Avenue in Boston, where it's still being a historic house. The connection of Barrage to Harvard University also goes back to 1883, where he studied, he was an attorney, so he studied law at the Harvard University. But most of his wealth come from mining in Chile early in the 19th century, oil and mainly copper. He was well known for his passion collecting plants, not only tropical orchids. That was his main specialty, actually, tropical orchids. But he was also an avid mineral collector. He reconnected back to Harvard in 1912, and as you can see in here, he wrote a letter to the curator at that time of the Earth and Planetary Science Department, where he invited them to come and visit his collection, but he expressed his interest on creating a program so some students would get to study his gold collection and also get a prize at the end of the studies. This letter carries on asking many questions, which I found it very interesting because you ask, would any real good be accomplished? He also mentioned it would be, what was it? Is the amount, can you read it? Is the amount suggested sufficient to attract one or more bright students a year? He also shows strong interest on the Earth and Planetary Science curriculum and the number of students at that time. In any case, 35 years later, that collection made his way to the museum in a typical Bostonian winter day. And as you can see, he donated more than 1,500 specimens, but obviously there was one or two that needed special hand carry. And that special specimen, which I believe was on that box, was described in 1893 in a newspaper from Colorado called the Gray Divine. The description on that newspaper said that there is a gold in spiral, so it's a gold specimen that was found during 1887 in the Groundhog Mine in Colorado. The specimen weighs 8.5 ounces, and the estimated value was $160. So already quite a price at that time. And this is the specimen. So when we think about gold nuggets are rare. Gold crystals are rare, but gold spires are the rarest. And only few have been discovered, and this is considered the world's finest. And it is estimated that our Earth, the continental crust, has 5 milligrams of gold per 1 ton of rock. So we will need around 20,000 tons of rocks to create even the most modest wedding ring. However, under certain geological processes, hydrothermal fluids are able to leach and finally concentrate that gold, producing ore deposits. Thank you.
Thank you. It's great to be here and to be one of the speakers on this program. As I thought about what to say, what does rare really mean? How can we define some of these topics? I thought about the idea that we're full of type collections here. Each of those type collections is a special, whoops, we need to go forward here, is a special place in time where an object was collected. Sometimes the only object, the only example we have of those. They're all rare, they're all special. And it's how we use those, and these digital projects relate to that, that make them very special. So I thought I'd show you about 6,000 slides of types right now. Not really. I picked two examples that don't have to do with that kind of rarity, but rather relate to how it is that we document and discover materials within the collections. And both of these are fairly recent discoveries. Discoveries in the sense that we have had these collections, but we didn't understand their full significance until fairly recently. So the first of these, some of you may have some experience with these, but I want to point them out, tell you a little bit about what you're looking at here first. This is a wooden plaque, and the wooden plaque illustrates here an artist's rendering of a plant. It's a Japanese plant, and it's a timber-producing plant. So the plaque is here. It's a section of the wood. This is the back of the wood. And if you look at this, the frame is constructed here of pieces of that include the bark, and the corners are constructed of cross sections of a branch. So this item, we have 8 of these. They're in the Economic Botany collection. This item was in the collection, or these 8 were there, and we knew that they were special, but it was only after, in 2007, our library had set up a temporary exhibit. A Japanese botanist looked at one of these and said, I know that there are others of these, and connected the dots that we had not connected. And it turns out that there are indeed a number of collections of these, a big collection in Berlin, a privately held collection, a collection of these in Japan. And these were produced in the 1870s, and they were produced, we think, as teaching models so that they could be displayed and you could learn about the plant. And how wonderful. You get all of the important features that you need to identify a plant. You get the flowers, the fruits, the leaves. You get the actual wood, and you get the wood in the form in which we identify the plant. Characteristics of bark, cross sections, and so forth. So almost by accident, we discovered the connection here. One of our research associates was involved in writing and working on a paper dealing with these samples. As I say, there are a number of them around. Ours came to us through the zoologist, Edward Sylvester Morse, who was also director of the Peabody Essex Museum and also curator of Asian art at the MFA. Again, what are these and how do we think about these? Well, they're botany. They give us the characteristics that we need to know. They're art. Someone produced these and made them. They're craft. It was very special to be able to put these all together. They're objects that we use to learn. So you could learn the plant and you could learn its anatomy. And in the end, they're objects that we admire. So this is an example of documenting and working with our collections, a scholarly approach to understanding how it is that they were created, why they were created, and what they mean. Here's another example. Just last year, a visiting art professor was working on diatoms, and in the process of working through our collection, we came across some ambrotypes. Ambrotypes are really special ways of producing images, and these are microscopic images. They're among the first microscopic images of diatoms that exist. Diatoms are algae with silica walls. They're small, they're microscopic, and the nature of the walls drew in early naturalists who were using microscopes because they could check the resolution of their microscopes by looking at the ornamentations on the walls, on these silica walls. So this was really pretty cool. And Wayne Barra from New Zealand was able to look at these and document them for us. I'll point out that I'm showing two images here. I'm not sure how well you can see them. They're in these beautiful cases, and they have been preserved now by the Weissman Center for Preservation in the Harvard Library System, cleaned and preserved. I think this is the cleaned one. This is the pre-cleaning. The person responsible for this was Asa Eaton. He was, when he did this, he was a senior at Brown. I kind of like to think of this as a senior thesis project. Somehow he got connected with L.W. Bailey, who presented the paper here. And the paper describes how it is that he made these images, the way in which he built the camera, the way in which he exposed these wet slides that produced a single positive image. So no negative, a single positive image, each image unique. He talks about how he used light and what the light source was that allowed him to make these images. The paper was published in 1862. He did the work in 1861. Here's another set, and I think you can see some of these details that early microscopists may want to have seen to check the resolution on their scope. Again, conserved and unconserved and conserved here, showing this detailed image. And the fact that he was able to do this, he had a microscope that was of high resolution, but he built the camera, he built the equipment that he needed to be able to do this. And these were essentially languishing in our archives until we discovered their true significance. Now, you might hope that Eaton had gone on to wonderful things, become a botanist, studied diatoms, spent his life on this project. That didn't happen. Like many of our senior thesis writers, he left it behind. He fought in the Civil War. He went to Harvard Law School. He became a politician. He was very important in Rhode Island politics. But here, this instant in time, 1861, single images of, positive images of these diatoms. Really a fantastic thing. And I would only say that our collections are full of these materials that we haven't documented, we don't understand completely, that we need to look at and examine. And certainly all of these digital projects will help us in one way or another to fully understand what our collections are like. So in the end, our collections are full of rare and interesting objects, both discovered and probably as many undiscovered. Rarest of all are perhaps those collections that tell us about the world as it once existed, the vast numbers of collections made in places often that no longer can be collected and no longer worked on. So as we look at these rare materials, we can think about all sorts of ways in which they, in some ways, make us more human by understanding the stories. So thank you.
Good evening, everyone. That's the back. That's the back, I'm told. So I only have one specimen that I'm going to show you in the next few minutes. And I'm going to take a slightly different tack, which is to use my presentation just to remind you that as much as we have in our collections these spectacular specimens, rare, some common, historical import, that museums are very much remain about today and the future, and that there are still many, many collections being amassed and will continue to be amassed, and the information that we can get from them and the beauty of these collections will probably, or we hope, match if not exceed those of the ones that we've gotten in the past. You know, many people speak of the 17th and 18th centuries as the or 19th century as the age of discovery. Well, I actually believe that the 21st century is the age of discovery from natural history, and there's just amazing stuff that we're getting. Now, this is not such a rare specimen. Here it is on the shelf. This is an earthworm. Here's the jar that it's in. You can see it peeking out from below there. If you turn the jar around, there it is. Not the most magnificent of specimens. But and here we go to the record, the digital record of the specimen in our data management system, MCZ base. And you can see in the lower right a series of images of it, and in the upper right there you see a little map. We can do wonderful things with collections databases these days. This particular specimen, this shows the site of origin of this rare and exotic earthworm, which was collected at 26 Oxford Street just a couple of years ago. Some of our specimens have a little more exotic locales than this one. Nevertheless, this specimen was collected to generate the images that are shown in the lower right. And I'm just going to go in and show you examples of a couple of them. First, if you see, actually just this one right here, I'll show you this. Well, this is your standard textbook anatomical illustration of the insides of an earthworm. But it's actually for this purpose that specimen was collected. Our curator in the MCZ, Curator of Invertebrate Zoology, Gonzalo Girbet, was approached by a digital journal called Gigablog. It was featured by Gigablog. This is a publisher that is interested in promoting data science and digital imagery in an online journal. And they wanted to produce illustrations of this specimen using a very advanced but now routinely used imaging technique called confocal computed tomography, CT scanning. This is now widely used in all kinds of fields, and it's increasingly used in natural history collections. And it's a kind of non-destructive imaging. It's a very high-tech X-ray, very much more sophisticated X-ray that lets you generate three-dimensional images of specimens without hurting them, and differentially coloring them so you can see them in tremendous detail. Here is one of the images that they produced, and now I'm going to go out of PowerPoint and show you a different version of this. So if you bear with me for a moment. Here is I'm going to show you some scans. So this is the resulting of the CT scanning, and there's the worm. And I should say, by the way, this is a PDF that you can download yourselves if you have if you can't sleep in the evenings or something and you want to play. This is available for free. You can download it to and you can then pull down all of these different views of this thing. And for instance, let's look at the nervous system, and you can start peeling away different pieces of the body. All of the different organ systems are color-coded for you. So here's nervous system 1. There's nervous system 2. We're peeling away other things. Let's peel away even more. There's nervous system 3. And by the way, you can grab this and move it around so you can look at it from all different angles. And there is, let's see, nervous system 4. It even comes pre-labeled for you, done by the publisher for their release. Another version of this, or another way to view this specimen, is shown here. And this is a movie taken from the scan. And we're going to basically start moving from one side of the specimen to the other. And you're looking, as this reveals, we're going basically deeper into the specimen, revealing the very detailed anatomy, internal anatomy of this earthworm. And we're right about in the middle of it now. And we're going towards the back. And you can see, we're looking up at the head end, up at the top there, and there's all the chambers right behind the head. And I think, let's say we're going to come back. Yes, we're going to come back in the opposite direction. I'm going to try to move this, advance it forward a little bit to expedite things. Oops, too far. And there we go. Then it actually will turn around. It'll rotate and turn on its, now it's sitting on its belly. And now we're going to go through the specimen from the side. And again, you can see all of the very intricate, detailed anatomy of this specimen. Now, this particular preparation took a lot of time, but there's no reason why this same technique cannot be applied to any specimen, any of the 21 million specimens in our collection, or thereabouts. And you can see the tremendous benefits. They're aesthetically beautiful, but they're also rich in scientific content. And this is the kind of special treatment, I think, that we will be doing a lot more. And I put it another way, if I can make an earthworm look as interesting as that, just think what we could do to things that actually have more spectacular intrinsic interest just from the start. So I think I'll stop there. Thank you.
Okay, I think this is working. Is this working? Okay, someone put their hand up and ask a question, and then I'll pass it down. Okay, over there.
That's right. And the patterns are species specific, and they're used in the taxonomy.
Yeah, I can barely see, so if you're putting your hand up, please wave it around. So, yeah.
So, question on the 3D worm. Yeah, so if you we're trying to simplify these images for like a younger audience or something, would you be able to actually go in and maybe change things and exaggerate them, like sort of close to make it easier for them to understand specific anatomy?
Let me try to repeat the question. If one wanted to, for the CT scans like that, simplify or modify the images, the short answer is yes. You have basically control. You can identify all of the structures you want and segment. You can remove some if you choose to. You can differentiate. Well, obviously it's all differentially colored, so you can color them whatever shape you want. They're used in all kinds of things right now. I should say another application they're being used is you can export those to 3D printers and make a simulated model of that generated from a CT scan. And that's being done in schools, in public schools.
Okay, another question. This are also, oh.
With all the collections moving or being put into new storage facilities, have you discovered anything recently that you didn't know you had? Like the ambrotypes or something, just in general?
The MCZ collections have been moved over to the Northwest building. Yeah, yes, I'll tell you a short anecdote about something that didn't come from the move. I'm the curator in herpetology, and we used to have on the, when you go in the office, a series of paintings or artworks, and I didn't, some photographs didn't pay much attention to them one day, at all, till one day one of them fell. It fell on the floor, and the frame broke and the glass broke, but the image was intact. And we picked it up and turned it around, and it had a card signed by Louie Agassiz, and it was a hand-drawn picture of a Matamata turtle from South America that was drawn by his private artist in 1871 that had been just hanging on the wall there for I don't know, 50 years, and nobody knew what it was, nobody bothered to turn it around. So we still find things like that occasionally.
A meteorite. We tried to move a big rock, and we couldn't. We got few guys to help, we couldn't. So we finally decided it has to be something unusual, and it was a big meteorite. But it was a label, and it's the one now on display, actually.
Tom, do you have any?
I think every time we open cabinets, we have the possibility of finding some of these things that are undiscovered. One of the interesting things, again, that involved one of our staff members, some years ago, a lichen was deposited in the collection, and it was kind of technicolor. And it ended up having gotten published or commented upon out in the literature, and the label on it said that it was from South America, but it was used in ritual rites, and it was supposedly hallucinogenic. And our research associate and others got into this project. Michaela Schmuel is the author of this. And it turns out that it has compounds that are hallucinogenic. It's the only lichen known to have hallucinogenic properties. But it turned up because of label data and information out in the literature, and then it got connected. But it was there in the collection all the time. And there is a paper on this now, right? Yes? Okay.
How was it?
Well, the problem is it's the only specimen, so if she'd eaten it, it would have been all over. We wouldn't have known.
Well, while other people are thinking, I'm just going to ask my question, which is really of Nancy, to say, what were the 2 or 3 things that you wish you could have put in the book that you had to cut out in the editing process? Or that Mark did, because I know you were working closely with him, the photographer.
Yes. Well, there was another thorough specimen that ended up as just a photo in the book. He'd collected a Blandings turtle in Concord, at Walden Pond, which I thought was very cool. And I spent weeks, I was in email contact with all these Thoreau scholars, and I went back through all of his journals trying to confirm that this was really collected by him. But he took bad notes. Like, he collected specimens and didn't write detailed descriptions of where and when he collected things. So in the end, all we could end up with was almost certainly. So it was a photo, but it couldn't actually be written about more extensively. And then we actually went as far as taking a photograph of a turkey and a bald eagle together, because we believed that Benjamin Franklin had believed that the turkey was the most appropriate, national symbol, right? And again, I bent over backwards, did all this research. This was before Google was so sophisticated. And it turned out to be completely false. Ben Franklin never thought that the turkey was the best candidate. So we have this beautiful photograph of these specimens from the museum together that we thought was going to be this great, sort of fun item, and it didn't matter.
Great. Anyone, any further questions? Otherwise, we can.
So I guess one question, a lot of the value of the book, I thought, is exposing the story behind the artifact. So the artifact is unique for scientific reasons or its uniqueness or whatever, but a lot of the interest is the human story, it's the collector or the discoverer or what have you. When you walk around the museum, I don't necessarily always get the same level of information. When I'm looking at the egg or I'm looking at the rock, it would be nice to know who found it, where, is there a story behind it? Is there a plan for the museum?
You need to buy the book.
I'm sorry?
You need to buy the book.
Okay. Can the museum, tell part of that story in the collection? I guess.
They're all pointing to me. Because So I think that the point you raise is an excellent one, because I know that for everyone, and maybe many people in the room, the most interesting time to go around a museum is with one of the curators or someone a scholar who knows things, and they point things out to you. The other person I should point out, because she's in the audience, is Blue Magruder, our PR person, who is also very good at taking you around the museum and telling you all sorts of stories. But yes, you're right. And Nancy's book, okay. We've got Nancy's book. And I think that that's one of the things that we struggle with, is how can we give that experience to people who are just visiting by themselves. So a lot of museums have tried to, who do things using our own iPhone and sort of tours, that you can, audio tours and things like that. So we haven't done a lot of that, although we have started, there's now a digital tour for the Islands exhibit that gives a little more information. But even then, I think, especially those of us who are scientists, we tend to often focus on the science rather than the human stories, which I just loved what you said about the woman who wore the Hamling necklace, which now makes me wonder whether Raquel does it, when she's by herself. But we won't make you own up to that. But yeah, I think your point is really a good one, and we need to be thinking of ways to do that. And I don't know if any of Jim.
I'll just respond briefly. I think you raise an excellent point, and there is a tension in museum in exhibit design between putting out enough information so you can provide all these interesting stories about individual specimens, but then overwhelming the visitor. And this is not endemic to natural history museums by any means. They go through it to art museums as well, same kind of thing. And what you see is a compromise. It's the I guess the result of the expert opinion of the exhibit staff of enough information to give people some idea of what they're seeing, but not too much they're going to find it off-putting and they're going to just walk away.
I just want to say that the most dramatic example for me is the mastodon, because there's a murder associated with that mastodon, and it's a really juicy, wonderful story. And whenever I give a tour, I just love stopping there to tell people that story. And there's no indication in the case at all. And I always think there should be a little asterisk or something that says, like, see murder.
Now you have to tell us the story, Nancy.
Oh.
If you can, very short.
Very short. Okay.
Because we've all seen that, or will see. You can see the mastodon.
Yes, the mastodon is fantastic. So John White Webster was a mineralogist here, and he really badly wanted that mastodon for Harvard, and it was going to cost $3,000 back in the 1840s, I think, which was a lot of money. So he needed to raise money, and he kind of took up a collection, and then some people didn't pay up, so he turned to a guy named George Parkman, who was a physician and a philanthropist, for help collecting the money. And then John White Webster, who was a bit of a spendthrift himself, turned to George Parkman and borrowed money from him himself. And it turned out that he put up as collateral his collection of minerals, and Parkman later found out that that same collection of minerals had already been put up as collateral to Parkman's own brother-in-law. So Parkman was really pissed. And he was one of those, I think, sort of nasty, rock-ribbed, Yankee types. So he hounded Webster and sat in the front row at his lectures, and stared at him and followed him around. And then Parkman disappeared. And weeks later, a janitor who had some suspicions found Parkman's bones and teeth in Webster's furnace, and some more bones in a chamber beneath his laboratory. And it was really fascinating because there were no witnesses. And in the end, Webster was convicted entirely on circumstantial evidence, which was kind of a legal precedent. And he was hanged. So can you fit that on a label and put it in the mastodon case? I don't know, but it's a really great story.
And we have his mineralized specimens in the collection. So if you want to get a bit freaked out, you see the label.
All right, well, I think we should stop now. So thank you all. I hope you'll join us upstairs.